Welcome to our deep dive today into quantum thermometry. We're going to be looking at an essay by Jurgo Schneeppert on this really kind of revolutionary way of measuring temperature. And, temperature is so fundamental to so many fields,
Right.
from just everyday life to cutting-edge science. But what happens when we need to measure the temperature of something incredibly small, like a single cell or a nanoscale device?
That's where traditional thermometers, which rely on macroscopic properties, hit their limit. They just lack the precision and sensitivity needed at such tiny scales.
Schneeppert argues that quantum mechanics offers a solution. But I got to be honest with you, the idea of using quantum phenomena to measure something as basic as temperature seems mind-boggling to me. Can you help break that down?
Sure, so it's all about leveraging the unique properties of quantum systems. So instead of relying on, say, the expansion of mercury in a glass tube, we're tapping into the inherent fluctuations
Of a quantum system.
So we're essentially using
A noise.
of the quantum world.
As a signal.
Precisely. Quantum systems are never truly at rest. They exhibit constant fluctuations in energy, even at absolute zero. And by carefully analyzing these fluctuations, we can extract incredibly precise temperature reading.
Okay, I'm starting to see how this works, but what kind of quantum thermometers are we talking about here? What are the tools of the trade?
So Schneeppert highlights several exciting technologies. One that stands out is the use of qubits, the building blocks of quantum computers, as temperature sensors. Qubits are exceptionally sensitive to their environment, making them ideal for detecting subtle temperature changes.
Now, I know qubits are usually associated with super cold environments. Does that mean that quantum thermometry is limited to ultra-low temperature?
Not at all. While qubits excel in those extreme conditions, other quantum systems can operate at a wide range of temperatures. Take NV centers in diamonds, for example.
Weight defects in diamonds can be used as thermometers. That's wild.
It sounds strange, but these specific defects, called nitrogen vacancy centers, have unique quantum properties that make them incredibly sensitive to temperature. They actually fluoresce when hit with light, and the intensity of that fluorescence changes directly with temperature.
So we're essentially shining a light
Yeah.
on a diamond and reading its temperature based on how brightly it glows. I have to admit, that's pretty cool.
Yeah.
But why diamonds? Are they the only material that can do this?
So diamonds are particularly stable, even at extreme temperatures, which makes them attractive for various applications, but Schneeppert also discusses other promising technologies, like right-ordered atoms. These are atoms with electrons in highly excited states, making them extremely sensitive to external fields, including temperature.
So there's a whole zoo of quantum systems that we can use as thermometers.
Exactly. And each technology has its own strengths and weaknesses, making it suitable for different applications. But they all share this incredible precision that comes from leveraging quantum phenomena.
This is all fascinating. But I'm curious, how does this translate into real-world applications? Who needs to measure temperature with such extreme precision at the atomic level, and why?
That's where things get really exciting. Imagine being able to measure the temperature inside a single living cell without disrupting it. This could revolutionize our understanding of cellular processes and disease mechanisms.
That's incredible. We could literally watch the temperature change as cells go about their business. What does Schneeppert say about this?
He highlights a study where researchers used NV centers to track temperature gradients within individual mitochondria, the powerhouses of cells. This level of detail could offer unprecedented insights into how cells produce and use energy.
So we're not just measuring temperature, we're gaining a deeper understanding of the fundamental processes of life. It sounds like this could be a game changer for fields like biomedicine and nanotechnology.
Absolutely. And beyond biomedicine, Schneeppert discusses applications in nanotechnology. Imagine being able to analyze the thermal properties of nanoscale components in real time. This could be crucial for designing more efficient and powerful electronic devices.
So it's not just about the precision of the measurement.
Yeah.
But also the scale at which we can make those measurements.
Right.
It opens up a whole new world of possibilities.
Right.
But as with any new technology, I imagine there are challenges. What are some of the hurdles that quantum thermometry faces?
One of the biggest challenges is noise. Remember, we're dealing with incredibly delicate quantum phenomena. Any interference from the environment can disrupt our measurements and obscure the signals we're trying to detect.
So it's like trying to hear a whisper in a hurricane.
That's a good analogy. Sources of noise can come from various places. Thermal fluctuations in the surroundings, vibrations, electromagnetic interference, even the inherent quantum noise of the system itself.
And I can see how that would be a constant battle for researchers. What are some strategies for overcoming this noise problem?
So Schneepat highlights several approaches. One is to develop even more sensitive quantum sensors that can better distinguish the signal from the noise. Another is to improve isolation techniques, shielding the quantum system from external disturbances. And of course, there's always ongoing work on developing sophisticated algorithms to filter out noise from the measurement data.
It sounds like a multi-pronged approach is needed, combining improvements in hardware, isolation techniques, and data processing. But beyond noise, are there other challenges? What about cost and accessibility?
Those are valid concerns. Currently, many quantum thermometry techniques require expensive materials and specialized equipment. For example, creating NV centers in diamonds often involves sophisticated processes like ion implantation and maintaining the ultra-low temperatures needed for some qubit-based sensors can be energy-intensive and costly.
So it's not exactly a technology that you can pick up
Yeah.
at your local hardware store just yet.
Not quite. But Schneepat points out that researchers are actively working on making the technology more accessible and affordable. They're exploring new materials that could offer similar capabilities as diamonds, but at a lower cost. And they're developing miniaturized systems that could potentially reduce the need for bulky and expensive equipment.
That makes sense. As with any new technology, we can expect to see significant advances in miniaturization and cost reduction over time. But what about the bigger picture? Schneepat talks about a future where quantum thermometry is integrated with other emerging technologies like quantum computing and artificial intelligence. What does that look like?
That's where things get really futuristic. Quantum computers could potentially revolutionize quantum thermometry in several ways. For example, they could be used to simulate complex thermodynamic systems, helping researchers to design even more sensitive and accurate quantum thermometers.
So we're talking about using one quantum technology to improve another. That's fascinating.
Exactly. And artificial intelligence could also play a major role. AI algorithms are incredibly adept at analyzing large data sets and identifying patterns. They could be used to sift through the vast amounts of data generated by quantum thermometers, extracting valuable insights, and potentially even predicting future temperature changes.
It's like having a superpowered research assistant, constantly analyzing the data and looking for hidden trends. That could be incredibly powerful, especially when you think about applications like climate monitoring or predicting natural disasters.
Schneepat even envisions a global network of interconnected quantum thermometers, constantly monitoring temperature changes across the planet and providing unprecedented insights into Earth's climate system.
Wow, this is a bold vision. But I have to ask, are there any potential downsides to such pervasive temperature monitoring? Could there be privacy concerns?
Those are important considerations, but they fall outside the scope of Schneepat's essay. He focuses primarily on the scientific and technological aspects of quantum thermometry.
Fair enough. It's always important to think about the broader implications of any new technology, even one as seemingly benign as temperature measurement. But focusing back on Schneepat's vision, what are some of the technological hurdles that would need to be overcome to make this global network a reality?
One key challenge would be communication. To create a truly interconnected network, we'd need reliable and secure ways to transmit data between quantum thermometers across vast distances. That might involve advances in quantum communication technologies, like quantum teleportation or quantum key distribution.
So we're not just talking about a network of sensors, but also a network of quantum communication channels.
Precisely. And then there's the issue of data processing. This global network would generate massive amounts of data. We'd need sophisticated algorithms and computing infrastructure to make sense of it all.
It sounds like a truly ambitious undertaking, requiring breakthroughs in multiple areas of quantum technology. But if it could be achieved, the potential benefits for understanding and managing our planet's climate would be immense.
Absolutely, and that's what makes quantum thermometry so exciting. It's a technology with the potential to revolutionize not just scientific research, but also our understanding of the world around us.
It's amazing to think that we can now measure temperature at such incredible scales, from individual molecules to the entire planet. It really highlights the transformative power of quantum mechanics.
Yeah, it's a testament to human ingenuity and our relentless pursuit of knowledge. Who would have thought that the strange and counterintuitive world of quantum mechanics would lead to such practical and groundbreaking applications?
It makes you wonder what other amazing applications of quantum thermometry are just waiting to be discovered maybe we'll be using it, to study distant stars,
Right.
or even to probe the mysteries of dark matter. What does Schneepat say about future directions for the field?
Well, he emphasizes that quantum thermometry is still a relatively young field with immense potential for growth. He expects to see continued progress in sensor development, noise reduction techniques, and integration with other quantum technologies.
So it sounds like we're just at the beginning of this quantum thermometry revolution. There's so much more to explore and discover.
Exactly, and that's what makes it such an exciting field to be a part of. There are countless unanswered questions and endless possibilities for innovation.
Well, a huge thank you to Jorgo Schneepat for providing such a fascinating glimpse into this world. His essay offers a compelling vision for the future of quantum thermometry.
Yeah, it's a field that's poised to transform our understanding of temperature and its role in the universe, and it's a fantastic example of how quantum mechanics is moving from the realm of theory into the world of practical applications.
So to our listeners, we leave you with this thought. What other groundbreaking applications of quantum thermometry can you envision? Let your imagination run wild. Maybe you'll be the one to unlock the next quantum leap in this incredible field.
Keep exploring, keep questioning, and keep diving deep into the wonders of the quantum world.
That's it for our deep dive into quantum thermometry. Until next time, stay curious.